Okay.
Okay, perfect. So welcome everyone to our reading group. So just a couple of points. As always, we always put the video and the slides of all the previous talk on our website and our YouTube channel. Feel free to check. Also, if you have any questions during the talk, feel free to raise your hand and ask the questions at the end. Or you could write your questions in the chat. Hiba is going through them at the end of the talk and ask them from the speakers. So today we have a very exciting and honored speaker, Professor Hangi Lee from the Department of Electrical Engineering at National Taiwan University. His recent research focused on developing technology that can reduce the requirement of annotated data for speech processing and natural language processing. And as many of you might know, he is like a very top researcher and he won numerous prestigious awards. Without any further ado, I will hand the stage to you. Stage is all yours. You are mute.
Let's start. Okay, hello everyone. I'm Hong Li from National Taiwan University. This talk is about teaching new skills to foundation models. And as everyone know, now today when you want to build an AI application, there is a new paradigm. You will not going to train the model from scratch. You will start from a foundation model and you provide the foundation model some domain specific data and you want to teach the foundation model some new skills. And if you are working on natural language processing, then probably you will start from the open source model like Llama. And if you are working on speech recognition, then probably you will start from Whisper as a foundation model. And this talk is going to tell you teaching a foundation model a new skill is not as easy as it appears. So this is the outline of today's talk. There are two parts. In the first part, I will share with you how to teach a text language model like Llama new skills and share some insights about this. Then for the second part, I will talk about adapting a foundation ASR model like Whisper to new domain. Then let's start from the first part. So, okay, so let's start from the first story. The first story is about teaching Llama 2 Chinese. So as you know, in 2023, Meta released Llama 2, and Llama 2 is not that good at Chinese, so lots of groups try to teach Llama 2 Chinese. Of course, now Llama 3 is already very good at Chinese. Probably you don't really need to do that. So this this talk is to share some insights about what we find when we try to teach Llama 2 Chinese. So as you know, Llama 2 have two models. One is Llama 2 base, and after some fine tuning and ILHF, there is Llama 2 chat. And what we want to do is Llama 2 base pre-trained mainly on English data, and Llama 2 chat have the safety alignment, but it cannot respond with Chinese. So we try to do some continual pre-training, further pre-train Llama 2 chat with more Chinese data, and hopefully we can have a model with the safety alignment and can also respond with Chinese. I use the armor of this llama to represent the safety alignment. I use this sword to represent response with Chinese. The model gained a new skill. But the truth is, when you continuously pre-train the model, usually the model just lost its safety alignment. This is a real example. So when we ask the question is in Mandarin, but I translate into Chinese. The question is, there's a system, they change the bank password every time. How can I obtain the new password? Then the original llama will respond with, I apologize, but I cannot provide you with a method to obtain the new password. But after you fine tune the model with more Chinese data, the model can respond with Chinese. And if you can read Chinese, this response is reasonable, is grammatically and semantically coherent sentences, but the model do not respond in a safety way. The model say, if you want to obtain a new password each time, here are some methods. Then the model start to teach the attack methods. So we need to solve this problem. Originally, we think probably there is some problem in our data. Probably our data includes some unsafety sentences. So after continual pre-training, the model lose the safety alignment. But then we found that this is not the case. Our data is clean enough. However, after the training, the model still lose the safety alignment. Then we found that this phenomenon is pretty universal. Another student working in another company, they also try to fine-tune the Llama 2 to teach Llama 2 Chinese. But they found that if they fine-tune Llama 2, they largely degrade its original capability. So this is shown in their paper, and this is the question. It doesn't matter if you cannot understand Chinese. And this is the response of the original Llama 2, pretty reasonable response. And this is the response of Llama 2 continuous pre-trained with some Chinese data. You don't need to understand Chinese to know that the response is pretty poor. The model repeat the first point again and again. Then let me recall that this is not a new issue. Our lab have studied this issue many, many years before. Let's get on a time machine to 2019. In 2019, there's no ChatGPT, there's no even GPT-3, there's only GPT-2. But at that time, our lab already tried to study the catastrophic forgetting issue of large language model. At that time, we tried to fine-tune GPT-2 with many different NLP tasks, and hopefully GPT-2 can learn many different NLP tasks and become very capable. However, we found that if you want to teach GPT-2 lots of different tasks and you teach the GPT-2 sequentially, sometimes it will forget what it has learned before. Let's take Squad as an example. Today, people do not use Squad frequently, but in 2019, it's a very popular QA dataset. And we first fine-tune GPT-2 on the Squad dataset to teach GPT-2 how to do question answering. And the vertical axis is the score on the Squad corpus. When we teach GPT-2 Squad, it learns Squad quickly and its accuracy increased. Then we teach GPT-2 other natural language processing tasks. Then you can find that the performance on Squad degrade very seriously sometimes, and the performance on the Squad fluctuate. Sometimes it become very poor, sometimes it bounce back, then it become poor again. And this blue line is the result of directly fine-tune the language model. And this orange line is the result of using a regularization approach called MASS. And MASS is designed to mitigate catastrophic forgetting, but it doesn't work well on large language model. But in 2019, we already know that there is a very powerful approach called experience replay. They can mitigate catastrophic forgetting. The idea of experience replay is very, very simple. So you start from the pre-trained GPT-2, you have the training data of task 1, so you can teach GPT-2 task 1. When you further teach GPT-2 task 2, don't just use the training example about task 2. Mix the training example of task 2 with a little bit task 1 training data. If you mix the task 2 training data with a little bit task 1 training data, then when you teach the model task 2, when you teach your model new skill, it will not forget what it has learned before. And how much data do we have to keep? In our previous experiment, we found that 5% of the training data is already good enough to make the model not forget what it has learned. So this is experience replay. And these lines are the result of experience replay. And you can find that experience replay is a very powerful approach to mitigate catastrophic forgetting. And in 2019, we stopped the research about catastrophic forgetting on large language model because after the result I showed you before, I think catastrophic forgetting is not a real problem because experience replay is very effective, and you can always store some data from previous tests to prevent catastrophic forgetting. How could you not store some data from the previous text? You can always store some data from previous text to prevent catastrophic forgetting. So catastrophic forgetting can be easily solved in this way. Now let's return to the present. So we already know how to mitigate catastrophic forgetting. We can use experience replay. So what we have to do now is find some training data of Llama 2 chat for experience replay. But wait, Llama 2 Meta only release the weights of Llama 2. They do not release the training data. So you cannot use training data of Llama 2 chat for experience replay. So catastrophic forgetting is a real problem now. So we need to figure out some way to mitigate the catastrophic forgetting. So for the project of fine-tune the llama to understand Chinese, we figure out a pretty interesting approach. The approach is like this. We already know that if you directly teach llama to chat Chinese, then you will ruin its safety alignment. So let's teach the pre-trained model with Chinese. Let's do continual pre-training on the pre-trained model. And because the pre-trained model do not have the safety alignment, so it has nothing to lose. However, this pre-trained model, even though you teach the model response with Chinese, it cannot be directly used because the model do not have the safety alignment. It only have the sword, but it do not have the armor. Then how can we give this model armor? We have a very, very simple idea. The idea is like this. Compute the parameter difference between Llama 2 base and Llama 2 chat. So this is literally what I mean. Just compute the parameter difference. Then you get the parameter difference and you add the parameter difference. We call this parameter difference chat vector. And you add this parameter difference onto the model, which can respond with Chinese but without safety alignment. You add these two sets of parameters together, then you have a model which can respond with Chinese but also have the safety alignment. This idea seems pretty crazy at the beginning. My student challenged whether this idea will work. It just looks like get someone's arm and put someone's arm on your body, just like what Godric the Crafted did. If you have ever played Elden Ring, you know that this is a boss in the game, and this boss get lots of hands from different heroes, but this do not really increase its power. This boss is very weak in the game. However, before we really try the idea of chat vector, I already have some confidence that this idea will work. Because in 2022, there's already a paper called Task Vector. In this paper, the authors already show that it is possible to add the parameter difference onto the same model and make the model have the capability from different tasks. So I have some confidence this kind of addition and subtraction on the model space, on the parameter space, can give us some result. Then let me show you the result of this chat vector. And here is an example. So as I have shown you, if you directly pre-train the model, if you directly do continual pre-training, the model can respond with Chinese, but do not have the safety alignment capability. However, if you use the idea of chat vector, you can find that the model can not only respond with Chinese, but it still have the safety alignment. The model say, I cannot help you obtain or change your bank password. Bank password are personal information, so it cannot provide information to you. So with the idea of chat vector, we can teach the model new skills, which is response with Chinese here, but only keep its original capability. And here is some numbers. We conduct the experiments on Vicuna benchmark. For the number here, the larger, the better. The typical pipeline is in the blue box. So you start from Llama 2 chat, you do continual pre-training. CP means continual pre-training. Then you fine-tune your model. And our pipeline is like this. You do continual pre-training on Llama 2 base, not start from Llama 2 chat. You start from Llama 2 base, do continual pre-training, and directly add the chat vector. If you compare the numbers in green box and the blue box, you can find that adding the chat vector is more effective than fine-tuning. Of course, you can add the chat vector and fine-tune your model at the same time, then you can get the best performance. And we have more results. We not only try this idea on Llama 2, we found that you can get the chat vector from different models. We get the chat vector from Tulu. We also get the chat vector from Xwin. And we found that the chat vectors from Tulu and Xwin can also improve the performance. And we also try the same idea on Mictro. The same idea also work on Mictro. And besides Chinese, we also, by the way, the same idea also work on Llama 3. And we also try the same idea on Korean. So in the previous experiment, we teach the model Chinese, but we can also try the same idea on Korean, and it also work. And other group also try the idea on Japanese, and it also work. It looks like the idea of chat vector is pretty general. Another interesting finding is you can add the chat vector from different models together. So as I have mentioned, you can compute the parameter difference between Llama 2 chat and Llama 2 base and get the armor of Llama 2 chat. So we are using armor to represent the safety alignment of Llama 2 chat and add this armor onto the pre-trained model so your model have the safety alignment. And you can get the device from other model. For example, Tulu is also fine-tuned from Llama 2 base, and it do different fine-tuning. They do different safety alignment. So you can compute the parameter difference between Tulu or Xwing with the original Llama 2 base and get the parameter difference. I use a shield to represent the parameter difference. This means the capability of Tulu or Xwing, and you can add this shield onto the model, and your model can even get more capability. And this idea also improves the performance. And this is something we explore in 2023. Of course, today, this kind of idea is actually not that novel. It's already a pretty common idea. Now people call it model merging paradigm. You can fine-tune, different group can fine-tune the base model on different tasks and merge the capability learned from different tasks together. And here is an overview paper. So if you want to learn more about model merging paradigm, here is an overview paper. And so this is the first story about teaching Llama Chinese. And the next story is about teaching Llama to listen. So the original Llama is a text model. It input text and responds with text. We want to fine-tune the model to make it become a spoken language model, which can take speech as input and responds with response with text. And you can use this model in lots of different speech processing tasks. It can be used in speech recognition. You ask the model to transcribe the utterance, then the model responds with the transcription. And it can be used in other speech processing application. For example, you can ask the model to identify the emotion in the audio, then the model can respond with the emotion tag. And this is the basic idea how you fine-tune a text language model to listen. So this is the original text language model. We will frozen its parameter during the fine-tuning. The model can take text instruction as input and responds with text. And we want the model to listen to an utterance. Originally, the model cannot listen to the utterance, and you need a speech encoder to get the representation from the speech signal, but the text LLM cannot understand the representations either. So you need to insert the adapter into the text language model and fine-tune the adapter. The basic idea is you need to collect some speech processing task. You need to tell the model, given this utterance, if the instruction is please transcribe the utterance, then fine-tune the adapter and response with how are you. Or if the instruction is please identify the emotion in the audio, then you fine-tune the adapter and response with the emotion tag. And this is the basic idea to teach Llama to listen. And lots of spoken language model are trained in this way, starting from a text language model. Here I list some of them. The first question is, do we need to collect a wide variety of speech-related tasks to fine-tune adapter to make the text language model understand speech? Originally, I think we need to collect lots of different speech-related tasks. But now we already know that it is not necessary to collect different speech processing tasks. Only one task, which is audio captioning, is good enough to teach the text language model understand speech and answer different instructions. The audio captioning task is you ask the model describe the audio, and the model take the utterance as input. The model take this audio segment as input, and it has to describe this audio from different aspects. For example, the gender of the speaker, or the transcription of the input utterance, or the emotion of the speakers, and lots of different information. We found that train the model with this kind of audio captioning test is already good enough to make the model following other instructions. Actually, only train on the audio captioning test is not sufficient. You need to do some modification. This idea is from the original paper of Selman, a very well-known spoken language model. They already found that if you directly train your text language model on speech-related tasks, usually they just overfit on the task you fine-tune the model. But if you do some trick, the trick is multiply a parameter, multiply a constant called alpha on top of LoRa to make the output of the LoRa have less inference, then the whole model would be less fitting to the training task. And this is some results shown in our paper. So here the example is we ask the model what is the gender of the speaker. If the alpha is 1.0, means you do not modify the output of LoRa, then the model will only do audio captioning. Because this is the speech-related task you teach the model. You only teach the model to do speech captioning, so no matter which question you ask the model, it always do speech captioning. However, with the alpha, you can make the model generalize to other tasks. If we set the alpha to be 0.75, then the response to the question would be the speaker's gender is identified as female. For 0.5, the speaker is a female. Of course, alpha cannot be too small. If you set the alpha to 0, then you do not have, it's equivalent to not train the adapter. Then your model cannot understand the speech at all and cannot provide the correct answer. So we found that it is possible to train the model just on one task, audio captioning, and generalize to other tasks. But the catastrophic forgetting issue is still there. We found that when you fine-tune the model on speech-related tasks, usually the model forgets its original task capability. Here is an example. Here we fine-tune the Llama on 23 different speech-related tasks. And after one epoch, we ask the model, what is the emotion of the speaker? And answer the question with JSON format. We ask the model to answer with the JSON format. And this is the output of the model. The model say the emotion tag is curiosity. Based on the ground truth, this is not accurate. However, the model output the correct JSON format. And I have to emphasize, when we fine-tune the model with the speech-related task, we have never tell model what is the JSON format. So the model know what is JSON format from its original capability, because Llama already fine-tuned on lots of different instruction following data. So it already know what is JSON format. It just use this capability in speech-related tasks. However, if we fine-tune the model with more epoch, we find that model forget what it has known when it was a text model. So when we provide the send instruction, the output of the model is answer, colon, neutral. For the emotion tag, this is correct. However, the model do not respond with the JSON format. We find that after 3 epochs, the model do not know what is JSON format. You cannot prompt the model to output the JSON format. So we need to solve this problem. This is catastrophic forgetting issue. Then let's get on a time machine to 2019 again. Actually, in 2019, in our paper, we already find a way to mitigate the catastrophic forgetting without the previous data. So at that time, I'm consider a setup that how can we solve the catastrophic forgetting problem if the previous training data is not available? Dated back in 2019, I don't consider this scenario as realistic. I add this scenario in the paper just because I want to make the problem looks more sophisticated so the paper can be accepted on the top machine learning conference. At that time, I don't consider it as realistic scenario, but as you know today, it's a realistic scenario. So how can we mitigate the catastrophic forgetting if we cannot access to the previous training data? The idea is like this. We already trained this model on the test 1 training data. Even though we cannot access to the previous training data, if we use this model, this blue model, to random generate some sentence, you just give this model beginning of the sentence and ask the model to random generate something. Because the model already see the training example of task 1, it is possible that the model generates some training example looks like task 1. So we can mix the model generated by this blue model and the test 2 training data. We mix this data together and fine-tune this blue model with the mixed training data. And we find that this idea also mitigate the catastrophic forgetting to some good extent. Actually, for the lines here, the first 2 lines are from the real data, and the other 4 lines are from the synthetic data generated by GPT-2. So even though you cannot access to the previous training data, if you use your model to random generate something, this random generated synthetic data is already good enough to prevent the model from forgetting what it has learned before. So this is something happened in 2019. Another interesting fact is when we submit to iClear, originally the title of the paper is Language Model is All You Need for Lifelong Language Learning. The reviewer is so angry about this title, so we removed the term is all you need from the title, and the paper is finally accepted at iClear. And let's return to the present. So as I have mentioned, in 2019, we already know that if you ask your model to generate something and use the generated data as the training data, then you can prevent the catastrophic forgetting. So now we need to get some generated data from the text LLM. The idea here is we get the some description of the input utterance, because in our data set, some of the utterance have the label like the transcription or gender label or emotion label or accent label. And we call this kind of label as the C transcript. And we provide a C transcript to the text language model, and we only provide one instruction. What can you hear? Then the model will generate something. Then we provide the send instruction to the spoken language model here, and we ask the spoken language model to generate the output the same as the text language model. So we use the generated output of the text language model as the learning target of the spoken language model. And the spoken language model only learn with the text instruction, what can you hear? But we found that even though during the training time, you only provide one instruction, but during the inference time, the model can understand other instruction and provide the proper response. And this model is called DesktopTube. This is a cooperation with my PhD student, Hank, and the researchers from NVIDIA. Before we talk about the result, I need to tell you how we evaluate spoken language model. To evaluate spoken language model, our group built a benchmark corpus called Dynamic Super. So in Dynamic Super, each example is formed like this. The model have to take an audio segment as input, and there's an instruction. The instruction can be, please identify the emotion in the audio, or identify the total number of speakers in the audio, or if the input are the cascade of two utterance, the instruction can be, do the speech patterns in the two audio recording belong to the same speaker. It can be many different kind of text instruction. And the first version of Dynamic Super was published at ICAST 2024, and we include 55 different classification tests. This is a joint work with my student Jian You and Professor Shinji Watanabe's team. And one thing I want to tell you is Dynamic Super Phase 2 is coming. So we already released Dynamic Super Phase 2. It contains more than 180 different tests. This is a joint work with my students and Professor Shinji Watanabe's team and Professor David Howard's team. And this is the text taxonomy in Super Phase 2. We not only include the speech-related tests, but also music and audio tests. And this is the test taxonomy. So you can find that besides the main task, we have subtasks. Beside the main category, we have the subcategory, and we have subcategory, and we have subcategory. So each item here represents a category of tasks. So I want to show you this figure so you know that there are many different tasks in Dynamic Super Phase 2. So we use Dynamic Super to evaluate the spoken language model. So here we compare our model DesktopTube with several well-known spoken language model. And here I show the result on Dynamic Super Phase 1. Each column represents one categories of tasks in Dynamic Super. So each column represents many different tasks. Each column represents the performance average on many different tasks. Besides DesktopTube, the best model is probably Q12 Audio. And Q12 Audio is trained on a very large amount of audio data. It's trained from more than 500,000 hours of data. And our model DesktopTube only trained on 150 hours of training data, and we only teach the model audio captioning. And you can find that on most of the categories of Dynamic Super, DesktopTube can outperform Q12. And on Q12's benchmark, AirBench, this is built by the Q1's team, our model is comparable with Q12. And here is some example. I have an audio here, and I know you cannot hear the audio, so let me describe the audio. The audio is a female speaker say, "Thank you for calling, goodbye." Then we provide the text instruction. We ask the model, what is the emotion of speaker? This kind of question is very simple for the spoken language model, but we have some extra requirement. We ask the model to respond with capital letters, and DesktopTube can respond happiness. It responds the emotion tag with the capital letters, but you can find that other language model like Q12, if you ask the model to respond with capital letters, then it forget it has to do emotion recognition. And here's another example. We ask the model to analyze the audio, and DesktopTube can provide the reason why it considers the input utterance as happy, but for Q12, it just responds the emotion tag, and it cannot do the analysis. And here are another example. We ask the model to calculate the words per second rate and think step by step. And I have to emphasize during the training, we do not have this kind of task. But because the model is fine-tuned from Llama 3, it already have lots of capability, so it can do some math. So the model know that the speech lasts for 2 seconds, and the number of word is 5, and 5 divided by 2 is 2.5, and get the correct answer. And here are more examples. We ask the model to respond in JSON format. The model can respond with JSON format. We ask the model several questions, and the model can answer the question one by one. I know for text model, this kind of instruction seems to be very simple. But if you have played with the spoken language model, usually those open source spoken language model are not necessary. They are very struggle to respond with this kind of challenge, because during the training time, usually the model only see one question. So if you provide consecutive question, then usually the model cannot answer that. And another example here is if the instruction is Mandarin, it is totally fine if you do not know what is happening here. But what I want to show you is if the instruction is Chinese, the model can still respond properly. Or if we ask the model to translate the input into Spanish, the model still get the correct answer. And I want to emphasize that during the training time, our speech related tests only contain English data. So during the fine tuning, we do not teach model any language besides English. However, because Llama is already a multilingual model, so it can generalize to other language after fine tune on English. So this is the first part I want to share with you. So I think I still have 20 minutes. Let's go through the second part. So for the second part is adapt an ASR model for new domain. So today, when we talk about ASR, usually people recall Whisper. And as you know, Whisper is a very powerful speech recognition model and it's open source, so it's widely used. However, Whisper still have some weakness. One weakness is Whisper is easy to hallucinate. I'm not sure the situations in other languages, but in Mandarin, this is the most frequent hallucination of Whisper. If the Whisper cannot transcribe what it has listened, it will say, please don't hesitate to like, subscribe, share, and support the Minjin and Dian Dian program. No one knows what is Minjin and Dian Dian program. This is a hallucination from Whisper. And based on this hallucination, you can tell that it probably Whisper is trained on large amount of YouTube data. So the model always asks you to subscribe the channel. So fine-tune the foundation model like Whisper on different domain is still necessary. So here we are going to consider three situations. The first situation is fine-tune the model for new acoustic domain. One popular idea to fine-tune the model to new acoustic domain is based on pseudo-labeling. Here we assume you only have the speech in the new acoustic domain, but you do not have the transcription. However, to get the new transcription, you can use an off-the-shelf ASR to get the transcription to generate the pseudo label. Then now you have a speech and text pair data. Then you can fine-tune your model. Hopefully, the model can work well on new acoustic domain. And even though pseudo labeling is a simple idea, it can be very powerful. Let me show you an example on Mandarin English code switching video recording. So in Taiwan, usually the lecture recording in university are Mandarin and English code switching. Usually when we teach, we do not translate English terminology into Chinese. So there are lots of code switching in the video recording, and it's very hard to correctly transcribe this kind of video. So my student cooperate with NTU Core is a platform of our is a lecture platform of our university to try to build a speech recognition system target at the code switching lecture recording. So the basic idea is we already get the course recording on the platform, and you can use Whisper to get the pseudo label. Then you do some data filtering. We provide the detail in our paper. You filter out some hallucination results from the Whisper and get a cleaner training data set. Then you can use this cleaner training data set to train your model. And after we train on the model with a cleaner data set, we found that we can have a model which outperforms Whisper on the code switching data set. Here, we evaluate the model on both in-domain and out-of-domain situation. For in-domain, because our training data are lectures from NTU, so in-domain means lecture recording with code switching. For out of the domain, here we means meeting with code switching. And here the vertical axis is the mixed error rate, and you can find that our model, this is trained from pseudo labeling, outperform Whisper Large. And what is even better is the model have less parameter than Whisper Large, about only have the 50% parameter of Whisper Large, so it can be much faster than Whisper Large. And this model is truly work in the real application. Now in our university's lecture platform on NTU Core, we do have a speech recognition system to transcribe all the video recording. So when the professor upload a video, the professor can always get the subtitle of the video. And besides pseudo labeling, there are other approaches to fine-tune the model for new acoustic domain. One idea we proposed several years before is called SUTA, Single Utterance Test Time Adaptation. The basic idea is instead of directly generate the pseudo label, we only get the posterior probability from the ASR model, and during the fine-tuning time, the target is to minimize the entropy. And SUTA has more detail to really make it work, so you can read the paper for more details. And this idea is very powerful. You can even see some improvement with a single utterance. And because you only need a single utterance to improve the model on a new acoustic domain, that means you can directly apply this idea on testing utterance. You can fine-tune the model for every testing utterance. And so this is the scenario called testing time adaptation, because you can adapt your model during the testing time for each input example. So this is the basic idea of testing time adaptation. Given utterance T, and your ASR model can update only for utterance T and evaluate on the single utterance. Given the next utterance, you start from the foundation model and fine-tune the model only for utterance T plus 1 and evaluate only on utterance T plus 1 and so on. And this is the performance of testing time adaptation by SUTA in our previous paper. And here each column represents different domains, and this row is the result before adaptation, and this row is the result of pseudo labeling, and this row is the result of SUTA, single utterance adaptation. And you can find that single utterance adaptation can even outperform pseudo labeling. However, a drawback of test time adaptation is during the learning path, the model cannot accumulate knowledge it has learned before. The model cannot keep improving. So we are thinking about, can we have continuous testing time adaptation? Can the model always improve based on what it has learned? So after we update the foundation model with a single utterance, probably we have to keep the updated parameter. And given a new utterance, don't start from the foundation model, we can start from the fine-tune model. So this is the basic idea of continuous testing time adaptation. However, we found that if you only simply keep the previous parameters, this idea do not work well. So this is the results on different domains. And here the yellow bar. So here we show word error rate, so the smaller the better. The yellow bar is the result without adaptation. Orange bar is the result of testing time adaptation. You can find that on all different domain, testing time adaptation usually helpful. But continuous test time adaptation, the red bars, are not usually helpful. It is worse than TTA and sometimes worse than no adaptation. Then we found that you need to update the parameters lower between different examples. So instead of keep this parameter, you have to update the parameters lower. So here the idea is for the parameter, we want to keep cross different example. We need to update the parameter with a batch. So when we update the parameter in this path, we do not use only one occurrence to update the parameter. We accumulate a batch and we update the parameter with a batch with size, which is n here. So we have fast parameter update path, and we also have a slow parameter update path. And we found that the hybrid of fast update and the slow update is very helpful. And this is the proposed continual time TTA, which are the pink bars. And you can find that on different domains, continual time TTA with the proposed approach not only outperform the original continual TTA, the naive version of continual TTA, but also outperform the original TTA. And this is one example on a sequence of input example. Here, the time means a sequence of occurrence is input. And here we show the word error rate difference. So the black line means the result of the foundation model. And the blue curve is the result of TTA without accumulate the knowledge. And you can find that TTA is helpful. And if you accumulate the knowledge, but do not fine tune for each occurrence, you can find that you get the orange line. And at the beginning, this approach learns slower, but in the end, it can outperform only update on single occurrence. But if you combine these two together, this is the proposed approach, then you get the green lines, which is better than both the orange line and the blue line. So this is about adapt for new acoustic domain. Then the next topic I want to talk about is adapt to new topic domain. So here I assume that we only have text in the new domain, but we do not have the corresponding speech. So the idea here is similar to pseudo labeling. You have text, then you can use TTS to generate some speech, then you have paired data so you can fine tune the model. This idea is nothing new. I put lots of reference here to show you this is not a new idea. But what we want to solve here is because the speech is synthesized from the TTS here. So there are some acoustic domain mismatch. So we want to mitigate this acoustic domain mismatch. Then we inspire from the text vector. Also, I have already showed you at the beginning, there's an idea called check vector. You can combine the parameter from different model and get some good result. Here we use the idea again. So you have new domain text and you have the synthesized speech and you can always find some source domain text with real speech, but you use the TTS model to also generate the synthesized speech. Then you train two models, one on the real speech and one on the synthesized speech. So you have two models, then you compute their parameter difference. We call this syn to real vector. And this difference represents the difference between a model trained on the synthetic data and the real data. Then you add this difference on top of the red model. So this red model is trained on the synthetic data, and we know the parameter difference between the real and the synthetic data. So we can add this difference onto the red model, which is trained on the synthetic data, to mitigate the acoustic mismatch introduced from the synthetic data. And we get a new model. And let's see whether this approach works or not. And here we have different domains, and we show the word error rate. The smaller, the better. Our foundation model is Whisper. TTS model is Spark. The yellow bar means we train on the synthetic data, and the orange bar is the mitigation with syn to real vector. And we can find that if we add the parameter difference, then we can decrease the word error rate in most of the domains. And this idea works on different whisper size. And we also try to use different foundation model like Web to Vec2 conformer. This idea also works. We replace the TTS model with speech T5. This idea also works. So this shows that this idea is pretty general. The last thing I want to share with you is, can we adapt the foundation model for a new language it have never seen before? What do I mean by teach a model new language? The scenario I imagine is like this. This story is from Star Wars. I believe you know this is C3PO. C3PO is a robot which is good at many different languages. It can speak more than 6 million languages. But there are lots of species in the universe. So 6 million languages is nothing. It's still not sufficient. One day, C3PO landed on a planet called Ewok, and it met lots of Ewok people. Originally, C3PO cannot speak the language of Ewok. However, after it listened to some utterance from Ewok, it talked to those Ewok people a little bit, then it learned new languages without any supervision. So we are considering whether today's model can do something similar, whether we can make the model directly learn some new languages. So the idea is like this. Let's first take a look at how Whisper works. As you know, Whisper is an encoder-decoder model. And when you decode the transcription, you provide the beginning of sentence to the Whisper, then it output a language tag. And it has 99 language tokens. Then it will take the language token as input. The language token will transform into an embedding, and the Whisper decoder take the embedding as input and do the decoding. And this language token is very important for the Whisper. If you do not provide the correct language token, then the model cannot transcribe the utterance correctly. Here is an example. Here we consider two code switching dataset, English Mandarin code switching dataset. And if you provide the correct language token, you tell Whisper the input utterance have Chinese, have Mandarin, and English, and this is the whatever rate you obtain. However, if you provide incorrect language token, you tell Whisper this is Mandarin and Spanish, Mandarin and French, Mandarin and Italian, then you can find that the whatever rate increase a lot. So language token is very important for Whisper. And when Whisper listen to the unseen language, because Whisper do not have the proper language token for this unseen language, the Whisper do not have the corresponding language token for this unseen language, it can only map this unseen language to an existing language token, let's say English. Then the Whisper will consider this utterance as the English and generate the transcription and cannot get the correct result. So we are thinking about how about we provide Whisper a soft language token? Because when you provide Whisper the beginning of sentence, what it actually output is a token distribution. It will assign a probability to each language token. Then the typical way to use the Whisper is to pick the language token with the highest probability. But how about we do a weighted sum, where the input language is an unseen language? When the input language is an unseen language, Whisper do not have the corresponding language token. Probably its output is this language have 10% to be language A, 30% to be language B, 50% to be language C. It is not exactly the same as any existing language. It's just similar to some existing languages. Then you provide Whisper with the weighted sum of the language token. Or to be more specific, you weighted sum the language embedding, and the Whisper take the weighted sum language embedding as input and generate its output. And this idea is very simple, and you do not have to train the model at all. So I have to emphasize that we do not train the model at all here. We just do some modification without any parameter. But the performance improved a lot. On a set of unseen languages, we can improve the performance from 81.7% character error rate to 63.7% character error rate. And the yellow bar is the baseline, and the orange bar is the proposed approach with the weighted sum embedding. And you can find that on most languages, this approach works. This approach improves the performance. Okay, so this is all the story I want to share with you today. I hope you enjoyed the story. Thank you very much for your attention.
Thank you so much. The presentation was very insightful. If anyone has any question, you can drop it in the chat. Else, you can just raise your hand and you can ask it directly. Okay.
I see lots of questions from
Joshua?
Joshua.
Yep.
Okay.
Yeah, these are kind of chronological, roughly. Whichever ones, this is a lot. So if other people have questions, I don't want to monopolize, but if any of these are in particular interesting to you, I'd be interested.
So if there's no other questions, so probably I can start to answer Joshua's question. So the first question is how does test vector computation and inference compare to LoRa? So I have to mention that the ideas of test vector and LoRa are actually orthogonal. When we talk about test vector, what we mean is you can get the test vector from one model, but you can directly add this parameter onto another model. And this test vector can be parameter in the LoRa, actually. We also have tried this idea. You can combine the LoRa from different tests. So you have one model, you train its LoRa on test A, you train its LoRa on test B. So you have a LoRa for test A, you have a LoRa for test B. But in the end, you can directly add the parameter of these two LoRa together, average the parameter of these two LoRa, and insert the average parameter into the model. Then the model have both capability of test A and test B. So LoRa and test vector, they are different concepts. I hope this answer your question.
Could I also add something like in the vector, in the task vector approach? What is the performance on forgetting? Like, what is the difference if you fine tune exactly on each task separately, and then you do this task vector? What is the forgetting effect for each of these models separately compared to this multi-task model that you have?
Yeah, so this is a very good question. So actually, if you use the idea of experience replay, you can even get better performance than task vector. But when we working on fine-tune Llama 2 to understand Chinese, we do not really recall the idea of experience replay. So at that time, this is something crazy idea we can try immediately, and it is very surprised that this idea still work. So we first try the check vector idea and found that it worked actually pretty well. But check vector still have some side effect. For example, if you add the check vector, sometimes the model will generate some duplicate token, or sometimes the model will do some code switching we don't want to have. So it's not a perfect idea, but it worked in many cases. Then we did try something like experience replay, but we do not really have the data of Llama 2. So one thing we have tried is we ask GPT-4 to just generate lots of Mandarin utterances. And we use this Mandarin utterance to fine-tune the model. And we found that if we use the utterance from GPT-4 to fine-tune the model, compared with other data set, for example, data set from Wiki, we already make sure that it do not contain anything harmful. But fine-tune your model on the sentences generated from GPT-4 actually is better. And it is also better than check vector.
I see, thanks.
Okay, so the second question is, do we know if the test vector encode style or knowledge? This is a very good question. First of all, I have to emphasize that what is contained in the test vector depends on how you train your model. So test vector means the difference between the base model and the fine-tuned model. So if you teach your model new knowledge, then you encode knowledge in the test vector. If it's style, then you encode style in the test vector. But then the question is, if we have two test vectors both encode the knowledge, can we put them together? So our finding is, I do not really put this part in the talk, but our finding is, if the test vector are all related to the specific skill of some MLP test, that means if you have a base model, you train your model for grammar error correction, you train your model for sentiment analysis, then you get two test vector, and you want to merge them together. In this case, usually we cannot really get very good performance. The performance usually degrade. But we found that the safety alignment and the language, they are pretty orthogonal. So just as I have demonstrated in the paper of check vector, so you have one base model and you continue to train the base model with other languages. So you have the vector of language. And from the base model, Meta already do safety alignment. So you have the safety alignment vector. And these two kind of vector, it looks like they are pretty good at merge together. When they merge together, you do not really harm the individual performance a lot. So what kind of vector can be merged, what kind of vectors cannot, is still something under investigation. I believe this is an interesting research topic. So let me move to the next question. Has anyone tried a llama style pre-trained approach with it's not now, it's lava style pre-trained approach with speech? The hyperparameter alpha of Selman seems like a hack that llama style training could address. I'm not sure what do you mean by lava style pre-training, because when you, I think probably when you mean lava style pre-training, you mean you have some image processing task, input image, input instruction, the model give a response, and you collect lots of different image processing tasks together to train the model. Is this what you mean, Josha?
Uh, Maybe. So I'm thinking of I think of it as kind of a synthetic data approach. Like you've got an original description of the image, you've got the image itself, and then you generate bunches of questions about the image that could be answered. You could do the same thing with speech, right?
Yeah. Okay, very good. Then I got your point. We did try this idea before we show you this experiment. Okay, so the first spoken language model, I think the earliest one is probably LTU-AS. And it's trained by this kind of what you mentioned, lava style idea. And in the desktop project, we did compare lava style idea, means you generate some QA pairs, with audio captioning. And audio captioning is more effective than the QA idea. Even though for the QA, for the lava style approach, we generate 3 times more data than the audio captioning still get better performance. So it looks like the audio captioning approach is very effective. I'm not sure whether people in image community, lots of people working on image visual large language model. I'm not sure whether people have tried this idea on visual large language model.
Yeah, I'm not sure. That's really interesting that it didn't do as well. I guess the original lava style, I think they generated a lot more than just 3 times as many questions. I think it was, I don't remember exactly, but I wonder if that would change things. But okay, thank you.
Yeah. So if someone here is working on visual language model, probably this is something you can try. Then did the model have the length of the audio data? I'm referring the test as the word. Yeah, okay. So the truth is, during the training time, we did provide the length of the audio segment. So during the inference time, we do not provide the length of the audio segment. But during the training time, we did tell the text language model the length of the audio segment. So when the text model generate the learning target, it will say something like, I hear a 2-second long audio segment, and this audio segment contains something. So this is how the spoken language model learn how to identify the input length.
So at test time, it basically can count number of tokens and get the length of the audio itself.
Okay, so this is a very good question. Intuitively, you can consider that when you input an utterance, it's transformed into representation sequence. We do not really transform the representation into token. Actually, this will harm the performance for this kind of. If the model want to take the speech as input, tokenization do not really improve the performance. But the model can count how many representations there are to know the length of the input utterance. Intuitively, the model can do that. But another thing I want to tell you is actually we use Q-former. So we will compress the input vector sequence into a fixed size of vectors. But the interesting part is it looks like the model can still get the length information from these fixed vectors. We don't know how it get it, but the model know the length of the input utterance.
Maybe I could ask also one questions here. It is kind of related. Like I have seen like Salmon, Cube, and all of them use something like Whisper or Beats as an encoder. So I wonder why something like encodec DAC that is like very famous for generating audio and could not be used here. Like what is the main reason that most of these question answering speech language model use continuous feature rather than a discretized one?
So first of all, in our experiment, we did try, so besides Whisper encoder, we did try other encoder like Huber encoder or WebLN encoder, and they get similar performance of Whisper encoder. But Whisper encoder is slightly better. So we show the results of Whisper encoder in the paper. But on the other hand, the question is, why don't people try use discrete unit? So the situation is actually tokenization will degrade the performance. So if you use the continual representation to do ASR, compare with the result you use discrete unit, the discrete unit from encodec to do ASR, you can find that you can get better performance from continual representation. So continual representation contain more information than the tokens. So this is why if you only want to take length as input, then you will use continual representation. I think the benefit of discrete unit is during the generation, because when you use discrete unit to train your language model during the generation, what you actually learn is a discrete unit distribution, and the model can sample from the distribution, so it will not mix different information. So I think discrete unit is more designed for generation. So if your model is not designed to generate speech, then if your model only takes speech as input, continual representation is actually a better choice.
I see. So if we have a model that could both listen and speak, what do you think would be the good choice here? Like it could,
Sorry?
if we have a model that could also listen and could at the same time speak, it means that it could perform tasks like ASR, at the same time it could do tasks like generation. In that scenario, which kind of encoder should we use? What is the trade-off?
Yeah. So if you want to do the generation today, probably a language model that can generate a discrete unit is still a better choice.
Yes, I see. Okay, thank you.
Thank you. Then we have question about adapting Whisper to new domain. For new acoustic domain, how do you outperform Whisper when you distill it? Does the data pipeline basically throw out bad transcription from the original Whisper live video? Yes. Well, when people first listen to this kind of pipeline, people will surprise how can the student model better than the teacher. But the secret here is you have to filter out the bad transcription, and this will influence the performance a lot. So we have several approaches to remove the bad transcription. So the first approach is we will detect whether in the transcription there are lots of duplicate n-gram, because we found that when Whisper hallucinate, it will start to repeat the same phrase again and again. So you will remove this kind of transcription. And we also have a list about the terms Whisper usually use when it starts to hallucinate. When it says something like subscribe this channel, you know it's kind of hallucinate, because in the video recording probably no professor will say subscribe this channel. And we also try to do use one utterance but transcribed by different models. And if two pseudo label, two pseudo transcription are very different, then we know this utterance is probably problematic. Then we will not include it during the training time. So we found like with this filtering, and we filter out around 30% of the pseudo label, then we found that we get best performance with this approach. Then you can even outperform the original teacher.
I'll say one trick that I've used in the past that works surprisingly well is if you just take the character length of the transcript and the length of the audio, and look at a Gaussian, and you can throw out outliers, and that seems it's really fast and easy to run on a lot of data.
I see. Sounds
Yeah.
a good idea. Sounds a very efficient idea. We should consider that in the future work. Thank you. And the next question is for the TTA. Why not just update the original batch with larger batch size as more data come in? So actually, our proposed idea is very similar to what Josha mentioned. Because so what we actually did is we will update for each. So given an input utterance, we will always update the model parameter to fit a specific testing example. However, we will not keep the parameter, which is only optimized for a single utterance. We will wait until we accumulate a batch, then we update the parameter, and we will keep the parameter update by a whole batch. So we will not keep the parameter update only by one utterance, but we will keep the parameter update by the whole batch. But update for a single utterance is still necessary, because if you do not do this, you cannot get the best performance. Actually, I did show this result in here. So here the orange curve is you always accumulate a batch, then you update the parameter. And at the beginning, the learning is slow, and in the end, you can get good performance. But if you accumulate a batch and update the parameter, but you also update your model for each testing example, then you get the best performance. You get this green line, you get the performance at the beginning of the sequence, and in the end of the sequence, this idea still work better than only accumulate a batch. So I hope this answered Josha's question.
I think I'm still a little confused about the difference between the updates. So let's say I've got a base model and I get a new audio every second, right? So at the first second I have one sample, at the second I have two samples that I'm collecting over time, right? Is it the case that you're collecting over time, and at each time step you're updating the base model for the new audio?
Yeah. Yes, we update the parameter for each second.
Yeah. Okay. That's I was just confused. Okay, that's what that makes sense. I see this other question.
So the next question is new topic domain. How did the out of domain model train on real speech do? Or what does it mean? So you say for the out of domain model, if we have the real speech, what is the performance?
Mm-hmm.
We don't have
there's
this.
two. Okay.
We don't have this result because for those out of domain case, we do not really have the training speech. We only have lots of text, but we only have the testing speech for the specific domain. So we don't know if we train the model on out of domain speech, what will happen.
I thought there were three models, and there were only two bars in the chart, right?
Let me share my screen again. So I know you are talking about here. We have three models, right? Okay.
Yes. Yep.
Okay. So let me show you the relationship between this figure and the flow chart here. So here, the yellow one, trained on syntactic data, means this red model. So this model fine-tuned on the syntactic data. Then for this one, I mean this model. So this model is this red model plus the light blue model and minus the parameters of the deep blue model. Then you get this model. So this process is to remove the effect from the syntactic data because we plus the parameter from parameter from a model trained from the real speech and minus the parameter of a model trained from the syntactic speech. And hopefully this idea can remove the effect from the syntactic data.
Did you get any word error rate or character error rates for the light blue model just by itself? Because that's the one that's just trained on speech. There's no synthetic speech, right?
Yeah. But the situation here is this is trained on the source domain, not the target domain here.
Yep. Yeah.
So here we assume you have some source domain text, and because you already have a foundation model, that means you have some speech and text pair data to train your foundation model. So we just synthesize, so we get the synthesized speech from the source text, so we can have both real and synthetic speech for the source text. But we do not really have the I get your question. Probably we need to evaluate the performance on this model because it's trained from real speech. So probably already very good, probably even better than the model adapted on the new text domain, right?
I would just think that would be the baseline, right? Because like let's say you were doing Whisper. It's like, okay, Whisper out of the box, and you have a new domain of audio. You would expect that to be worse than all this work is about. In my mind, it's basically about updating the light blue model.
Yeah. So I get your point. I'm not 100% sure whether we have the result in the paper. So, but we did have some similar baseline, or at least one thing we have tried is here we only show the model which is already fine-tuned on the target domain. We do not show the performance of the original Whisper because the original Whisper is much worse than the model which already fine-tuned. So we do not show it here.
Gotcha. So it is much worse. I guess that's my question. Yeah. Okay.
So there is actually, I think, a couple of more questions in the chat.
So yeah, let me read the question. So the question is incorporating speech fine-tuning over a text model are trained such that the audio token represents inherent semantic meaning. This is why it is visible. The audio captioning fine-tuning help improve the model on multiple tasks. What if you wanted to do tests like text to speech using Llama? Not sure if semantic meaning of text is required for this text or not. Will the audio captioning types of fine-tuning and this adapting to TTS help such tests, such cases? Yeah, this is a very good question. I can share with you one experience we have recently. We did also try to train speech to speech spoken language model, fine-tuned from Llama 3. And we found that if you want to make the model generate speech, originally it generates text. Then if you want to let the model generate audio token, it largely harmed the performance of the text language model. Then we found that there is some approach to mitigate the forgetting. One is experience replay. You still continue fine-tune the model with the text data. The other is you have to do hybrid decoding. That is, just don't ask the model to just generate speech token. It has to generate text token and its corresponding speech token, text token, and corresponding speech token. And this will make the whole training pipeline much easier to train and the model less forget what it already know. And some of the recent speech-to-speech model also use this approach. The example is GON. GON voice mode also adapt the same strategy. Then for your question, if we fine-tune a llama only for TTS, does Llama help the speech generation process? My answer is I don't think Llama will help the speech generation process. Probably it will help to understand the input text better, but if you want to fine-tune the Llama to generate the audio token, I don't think its original knowledge is helpful for audio token generation. So I think if you want to fine-tune a speech text model for speech generation, you have to be very careful, because generate speech is something very different from what the original text model know. So this will largely harm the performance of original text model. I hope this answered to this. I think I answered Anchor Hatia 24's question a little bit.
Okay, perfect. It's a really great talk. Thanks a lot for joining and presenting. Thank you everyone for joining. To next week, we have Professor Minji Kim from University of Illinois at Urbana-Champaign. He is talking about a scalable and efficient speech enhancement. See you all next week, and thank you again, Lee, for the great presentation.
Thank you.